We're now going to consider helium. And a big warning. Up to this point in the class, every single problem that we've considered has been exact. So the particle in the box, the simple harmonic oscillator, all the rotation stuff, even the hydrogen atom, the solutions that I presented for you, the functions, they might be complicated mathematical functions, but the energies have been exact. We know exactly what the wave function is. We can solve the thing with perfect accuracy using just the equations of 19th century mathematical physics. Those are all worked out, tabulated in big, thick books, everything. From now on, that's not true. So this is the last time we will be working with a problem where we know the exact answer, and the problem becomes approximation. So here's what we're going to do. What we're going to do is think about helium, neutral helium, where we have one nucleus, a charge plus Z, called Pauli, of course, and we're going to have two electrons. Here's Clarissa up here, and here is Juan over here. And each has a -1 charge. So the situation is that there's a central force potential between Pauli and Clarissa, an electrostatic force. The distance is going to be R1, that vector there, and the potential we're going to call V1. And actually, when you work it into the units, that potential is equal to -2 times the Rydberg constant times the charge of the nucleus Z over R1. So it just depends on 1 over R1, just like before. There's nothing different about this one. And it depends on the nuclear charge. So this problem that we're solving in general, just like we did for the hydrogen-like system, this is a helium-like system. The important part is that we have two electrons, and we need a nucleus with a charge plus Z. And in general, plus 2 is going to be what we're talking about for helium here. So then there's Juan over there. And Juan is at a distance R2, and it has an interaction potential with the nucleus as well. It's minus, again, negative, it's attractive, 2RH times the nuclear charge Z over R2, the distance from the nucleus to Juan. And that, again, is a straightforward potential. We've already addressed the problem. There's no big deal there. So we have Clarissa interacting with Pauli and Juan interacting with Pauli. They both want to do that. The attractive potential means that the energy goes down as they get closer together. It's confining. It's more stable if they're closer together, etc., etc., etc. There's no big deal with that. But then there is one huge deal, and that is Clarissa and Juan hate each other. And they also have an electrostatic interaction, and because they have like charges, both negative, that interaction, which goes like the distance R12 between them, which is the difference in the vectors R1 and R2. So Clarissa can be anywhere in space with an R theta and phi. Juan can be anywhere in space with an R theta and phi, and that positions them, and the difference, the distance between them, is the vector difference R1 minus R2. So it's Lord knows what, but it's going to be some number, and the interaction potential V12 is plus 2RH times 1 over R12. So that one is a positive sign, meaning it's a repulsive potential. They hate each other, they're trying to push each other away, and it's destabilizing the system. And that is what makes the problem hard, and in fact, no one has ever figured out how to solve it without approximations, and we're going to talk about those approximations. So it's the fact that Clarissa and Juan are hating on each other that really makes this an interesting and hard problem. So let's think about setting it up. So we're going to write down a potential like we always do, and it's going to be a potential of the coordinates of Clarissa and Juan. And we can write it as a potential of Clarissa, a potential of Juan, and an interaction between them. So we just take those three terms that we already had. They each have a 2RH in them. There's a minus Z over R1. There's a minus Z over R2. And then there's a positive 1 over R12. And I put absolute values around each of them because it's the distance. So it's the radial coordinate there. In spherical coordinates, R1 and R2, it's just the value of the radial coordinate. But again, to get the R12, we have to take a vector difference of the two full vectors of position, of location of Clarissa and Juan in space. So that's our interaction potential. And like always, we can then write down a Hamiltonian, which we'll do in a little bit. But let's look at this a little more. Again, we have these two negative signs. Those are attractive. And then we have the positive sign. And it's that R12 term there, that little R12, that has to do with the distance between Clarissa and Juan, and it depends on every one of the 6 other variables, the 6 independent variables that describe position. So R1, the Juan's position as a vector, has R1, the radial distance, theta 1, and phi 1. Actually, that's Clarissa, excuse me. Juan's position would be R2, and that's got, or position 2 has got a radius R2, a theta 2, and a phi 2. So there's 6 independent variables that can describe where Clarissa and Juan are simultaneously with respect to the nucleus. And Pauli, we're assuming, is basically infinitely massive here, and so we don't worry about Pauli moving around. So it's the R12 involves every single one of those coordinates. It's an awful coupling term. It's really, really hard to deal with. And so what we're going to do is we're going to break this potential up into 2 bits. We're going to call this 2 Rydberg constant of hydrogen, then it's a minus z over R1 minus z over R2, and then we're going to take the plus 2 Rydberg constant for hydrogen, a plus 1 over R12, and we're going to separate them out. And so the left-hand bit, we're going to call that V naught. And the right-hand bit, we're going to call that V prime, and actually we're going to call that H prime, as we'll see in a little bit. And the V naught is what we call the 0th order potential. So it's kind of our first guess. And the strategy here is when we're faced with a math problem that looks, in fact, like it is really, really hard, and it is really, really hard, but we see that, you know, if it just wasn't for that one awful part of the problem, it would be really, really easy. And then there's a hard bit. Well, we're lazy. Why don't we solve the really, really easy part and then break off the hard bit and see what we can do with it? So we're going to break out this what we call 0th order part, and we're going to call that a 0th order potential. And we're going to leave behind the bad thing, the R12 that couples all the coordinates of the system. And we call that the perturbation Hamiltonian in the trade. And you'll see why we call it H prime and not V prime in just a second. So that's how we set up the problem. As always, it's the potential energy, the interaction terms, that define the problem. Now we've got it set up, and we've broken it up so that we have this 0th order part, where Clarissa and Juan basically are just ignoring each other. You know, that's the best case scenario. They hate each other, and they have some sort of pact where they just totally ignore each other. And so their energy has everything to do with how close each individually is to Pauli, the proton there, the helium nucleus now. But there's nothing about the interaction of Juan and Clarissa at all. They don't like each other, but they don't pay any attention to each other. That turns out to be an easy problem. So we'll deal with that one first. And we leave behind, then, the hard bit, which is, okay, Juan and Clarissa really do hate each other. There is a positive, in other words, repulsive interaction associated with them. So once we've solved the easy bit, we can use the insights from that easy solution and turn around and solve the hard bit. Well, let's write down this Hamiltonian, identify the hard bit and the easy bit, pull out the easy bit, and solve it. All right? Well, H psi is equal to E psi. That's always the start. So now psi, the wave function, is a function of R1 and R2. And that's going to be equal to E times the wave function of R1 and R2. And those R's now are vectors, meaning that R is specifying the values R1, theta 1, and phi 1, the full coordinates of Clarissa, and R1, theta 1, and phi 2, R2, theta 2, and phi 2, the full coordinates of Juan. So the whole wave function is a wave function that describes the position in space of both electrons. So we've got a function, the probability, if we take the wave function squared, I'm going to know something about the probability of finding Clarissa here at some point and Juan there simultaneously. So R1 and R2, it's telling us about both electrons. And then there's an energy over here, and likewise, that's the total energy of the system. I don't really care about Clarissa's energy and Juan's energy. I care about the total energy of the electrons. So it's both electrons. And finally, again, that vector on R means that really represents the 3 coordinates that each electron can have. So Clarissa has coordinates R1, theta 1, and phi 1, and Juan has coordinates R2, theta 2, and phi 2. and we can use vector notation to represent that. So that's that. Now we're going to say, so this is the Hamiltonian is minus h bar squared over twice the reduced mass times the second derivative operating on psi plus the potential, and we've broken that up. We have a v naught times psi, and also this thing h prime times psi, the perturbation, and that's equal to the energy times psi. So the del squared part, the curvature part, actually has curvatures in both coordinates. So there's a second derivative in spherical coordinates describing how variable 1, or essentially how Clarissa's coordinates curve in space, and there's the corresponding curvature related to the second set of r2, theta 2, and phi 2. So the curvature acquires elements of both, but it's very much, they're separated. One is just the one coordinates, one is just the other coordinates. So we really can write it as the sum of those two. And that kind of motivates the possibility that we maybe can write the wave function itself as a function of R1 and a function of R2. And there'd be a psi 1 of R1 really and a psi 2 of R2, and those would be the independent wave functions that we'd multiply together just like any other separation of variables problem. In other words, we'd get the two separate wave functions for the single individual electrons, and it would look a whole lot maybe like 1s1 and 1s2, or we might identify that as 1s squared, 2 electrons, each in a 1s orbital, meaning each of the electrons has a 1s wave function, and we're thinking of them being as individually occupying those individual wave functions. And as we'll see, that's valid at the approximate level. It's actually not valid at the perturbation level, but we'll see a little bit more about that later. So if I leave behind the perturbation term h prime, this is an easy problem. So let's just toss it away. Let's solve an easier problem where I've got minus h bar squared over twice mass. I'm going to take over all the things having to do with R1 and put them on a left-hand side. So I've got del squared psi 1 psi 2 minus 2 times the Rydberg of z over R1 psi 1 psi 2 minus, I'll pull a part of the energy, E1 psi 1 psi 2. So I'm just going to take a portion of the energy over on the left-hand side. And then that's going to be equal to an equivalent, minus h bar squared over twice the reduced mass times the del 2, the coordinate in Juan's r theta and phi, psi 1 psi 2, minus 2 rh z over r2, the distance of Juan from the nucleus at phi 1 phi 2, psi 1 psi 2, and finally another component of energy I'm going to call E2 psi 1 psi 2. So I've separated out the left-hand side is operations having to do with the coordinate set 1, and the right-hand side is an operations having to do with the coordinate set 2. I still have the psi 1 and psi 2 and everything, and I got to get rid of them. So let's just divide everything by that, psi 1, psi 2, and psi 1, psi 2. Well, that's pretty useful because, first of all, let's look over at that del squared, del 1 squared there. That psi 2 isn't affected by that, so it comes out. And then I can divide out all of the psi 2's from the left-hand side. And likewise, I can divide out all of the psi 1's from the right-hand side. And now I really have separated the problem. Now I have something that looks like minus h bar squared over twice mu, and a curviness, del squared psi 1 over psi 1, minus twice the Rydberg constant of hydrogen, z over R1, and then a minus an E1. And I get the same thing on the right-hand side, formally with a minus sign. But so now I've completely separated the problem. I've got something that depends only in Clarissa coordinates on the left-hand side. And I have something that depends only on Juan coordinates on the right-hand side. And they have to be equal to each other. And once again, the only way that can be true is if they're equal to some number. And in this case, since I have energies right there in each side, we're just going to say that some number is basically 0. It's an offset, doesn't matter. It won't change. And so in fact, if each of these sides is equal to 0, that satisfies the condition. So I can take the equation on the left-hand side and say basically, ha! This is the hydrogen atom problem we already looked at. There's nothing different. It's got a z of 2, if we're dealing with helium, but it's just a hydrogenic problem. It's a single electron problem. There's nothing to do with any other electron in there. So I know the solutions. The energy is equal to minus z squared, Rydberg constant of hydrogen, 1 over n1 squared, where n1's a quantum number that goes 1, 2, 3, 4, 5, 6, 7 to infinity. That's it. There's another quantum number L for the total angular momentum, goes from 0 to n minus 1, and of course there's poor old m sub z, whose absolute value has to be less than or equal to L1. And the actual wave function, psi1, is going to be a 1s, a 2s, a 2p, a 3s, a 3p, a 3d, etc. Critically important, this is a solution to the zeroth order problem. But in this case, the single electron solution that we did for hydrogen still applies. Now I look over on the right-hand side, same thing. Lather, rinse, repeat. Exactly the same problem. There's just 2's instead of 1's. So this is Juan. Juan is a single electron. It's ignoring Clarissa. And so it as well is going to have the exact same set of answers, except they're in parallel. So the total energy is going to be the sum of the two solutions, and that's just minus z squared times the Rydberg constant. And there's a 1 over n1 squared plus a 1 over n2 squared. And n1 can go from 1 to infinity, and n2 can go independently from 1 to infinity. So they're totally independent. Now, if z is 2, if we're dealing with helium, and we're in the ground state, where n1 and n2 are both 1, then this becomes minus 8 Rydbergs. So that's the limiting case. Our guess, our first guess, our zeroth order guess for the solution is just that putting 2 electrons next to a helium nucleus makes the energy twice as negative. Remember, the answer for 1 electron next to helium is minus 4 Rydbergs. So we just did a whole boatload of math to show that if I have not 1 but 2 electrons next to helium and the electrons don't know about each other, I get twice the energy. It goes to minus 8 Rydbergs. It's not a very earth-shattering conclusion, but it's nice to get the answer. And then the wave function itself is the wave function of Clarissa times the wave function of Juan. So again, in the ground state, where n is equal to n1 equal n2 equal 1, this is a 1s1, 1s2. So this is the way that we write the wave function for both electrons in the ground state. Electron 1 has a mathematical function for a spatial distribution function. In other words, its wave function equal to the 1s function, basically e to the minus rho, and that's true as well for Juan. Exact same function. We can't tell the difference between them, and we'll learn about that a little more in a little bit.